So now let us start this chapter with the 3.7 point, which is periodic trends in properties of elements. So before this, we have studied why the periodic table is grouped into 4 blocks, S, P, D, and F, and also we have seen the metal, non-metals, and metalloids, how they are placed in the periodic table. So now we will be studying the trends in the properties of the elements. So by the periodic trends, we will be studying about the physical properties, that is the atomic radius, and then the covalent radius, followed by ionic radius, ionization enthalpy, must be electron gain enthalpy, and all of these physical properties we'll be dealing with in this particular topic. So there are many observable patterns in the physical and chemical properties of the elements as we descend in the group or move across the period in the periodic table. So either when we go down the group or ascend in the period, like left to right or right to left in the periodic table in a particular period. So they are very common trends. So, for example, within a period, chemical reactivities tends to be high in group 1 metals, lower in elements towards the middle of the table, and increases to the maximum in group 17, that is the non-metals. So likewise, within a group of representative metals, say alkali metals, reactivity increases on moving down the group. Whereas within a group of non-metals, say halogens, reactivity decreases down the group. Then why do the properties of elements follow these trends, and how can we explain the periodicity of such trends? To answer these questions, we must look into the theories of atomic structure and properties of the atoms. So in this section, we shall discuss the periodic trends in certain chemical and physical properties and try to explain them in terms of number of electrons and energy levels. So every physical properties, chemical properties, you can explain on the in the terms of number of electrons and the energy levels in the particular atom, right? So let us start with some physical properties. So there are numerous physical properties of elements such as melting point, boiling point, heat of fusion, vaporization, energy of atomization, etc., which shows periodic variations. However, we shall discuss the periodic trends with respect to atomic and ionic radii, ionization enthalpy, electronegative enthalpy, and electronegativity. So all of these things, how many things? Atomic radius, ionic radius, ionization enthalpy, electronic enthalpy, and electronegativity we are going to deal with. Okay, so most of the physical properties you'll see, you can easily define if you know the radius and the electronegativity. Every other property is linked with the size and the electronegativity of the element. So if you know the size trend and the electronegativity trend, then you know everything. And how they are correlated, we will be dealing with that in this chapter, in this particular section. So let us talk about the atomic radius. So first of all, before starting, I'm reading this chapter. We can, I would like you all to assume what you guys think that what could be the trend in the atomic radius when you go down the group or across the group. Since when you're going down the group, then the electron is added in the next higher shell. Okay, so basically the principal quantum number is increasing. So you are adding another shell. So definitely when you're going down the group, the size is increasing, right? And when you're going from left to right in a particular period, then what are you doing? You are adding one electron, okay? So you're adding one electron in that particular orbital. Okay, so what do you expect? Will there be like increase in the size or decrease in the size? So the answer to this, all of these will be dealing with this in this chapter, okay? So you can well imagine that finding the size of an atom is a lot more complicated than measuring the radius proton. Okay, yes, definitely, because ball has a rigid shape, but atoms doesn't have rigid shape, because like electrons are there. So which type of radius you want to like get information about? You want the covalent radius, you want the ionic radius, you want to which type of radius, right? So firstly, because the size of the atom is very, very small. Secondly, since the electron cloud surrounding the atom does not have a sharp boundary. So there is no such sharp boundary present in the atom, so that is why it's very difficult. And Therefore, there are a lot of like 2-3 types of radius that you need to study when you're dealing with atoms. So that is why, and because we don't have any rigid boundary in case of atoms, so all of these atomic radii, covalent radii, ionic radii, all of these are just, they're not precise. So in other words, there is no practical way by which the size of the individual atom can be measured accurately. Okay. So however, you can get the estimate of the atomic size, okay, by doing the distance between the atoms in the combined state. So like if you have a single atom like hydrogen, then you cannot find out the this radius of the atom. It is not possible. But when it is in the combined state, when it is, for example, H2, then you can, in that case, you can find out the radius. Okay. So one practical approach is to estimate the size of an atom of a non-metallic element is to measure the distance between two atoms when they are bound together by a single bond in a covalent molecule, and from this value, the covalent radius. So in that case, you get the covalent radius of the element. Okay. For example, as I told you about the H2, so from there also you will know the bond distance, right? So if you average the bond distance, then you get the radius of the atom. Okay, so there are various techniques by which you can actually find out the bond distance. There are various spectroscopic techniques. So once you know the bond distance between two atoms, then you can definitely average it out, and you get to know about the radius of the particular atom. Okay, so for example, in case of non-metals, you can have the covalent radius, and in case of metals, you have to define the metallic radius. So which is taken as half the equal distance separating the metal cores in the metallic crystal. Again, it is similar. For example, the distance between two adjacent copper atoms in solid copper is 256 ppm. Sorry, picometer. Hence, the metallic radius of copper is assigned a value of 128 picometer. For simplicity in this book, we use the term atomic radius to refer to both covalent or metallic radius, depending on whether the element is a non-metal or a metal. Okay. So, this atomic radius is a common term. It is used for both the covalent radius and the metallic radius. So when you have metal in your hand, then you define metallic radius, and when you have non-metal in your hand, then you define covalent radius. Okay. So as I told you, the atomic radius can be measured by X-ray or other spectroscopic methods. The atomic radius of few elements are listed in table 3.6. We don't have to remember all this, but this is just for information. So we can explain these trends in terms of nuclear charge and energy levels. But you can actually see the trend. Okay. So this is period number 2 from left to right. This is period number 3 from left to right. What you see. And obviously this is down. Okay. So from when you're going from left to right, then the energy is decreasing. Because you are adding only one electron in the valence shell. There is no increasing valence shell. There is a particular, the same valence shell, and you're just adding one more electron to it. But you're also increasing one positive charge also. Proton is also increasing, right? So we are increasing one proton and one electron. But the electron is added in the same shell. You're not adding any but another shell. Likewise, you're going down the room, you're adding shells, right? But here you're not adding it. So hence here the overall Z effective from the nucleus is increasing, and that is why the electrons are more towards the nucleus. That is the attractive force between the electron added and the nucleus is increasing when you go from left to right. Hence, there is a decrease in the radius that is observed, which can be seen from table 3.6 also. But as I told you, when you go down the group, then you are not just adding you're adding a lot of electrons, but the thing is that you're adding one more shell. So that will increase the radius between the electron, the last electron, and the nucleus. That is why overall radius of the element increases. Okay. So it is because, let us just see what is written in the book. So it is because within the period, so in the period what happens? Radius decreases. So it is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases. That is the Z effective I was talking about. Increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus within the family or periodic column of the periodic table. The atomic radius increases down the road. So regularly with the atomic number, as illustrated in figure 3.4b, for alkali metals and halogens, as we descend the group, the principal quantum number increases and the valence electrons are further from the nucleus. So this happens because the inner energy levels are filled with electrons, which serve to shield the outer electrons from the pull of the nucleus. Consequently, the size of the atoms increases as well. So it is the same. As I told you, that is the same explanation. It's very important. So note that the atomic radii of noble gases are not considered here. Okay. So being monoatomic, so you cannot actually get to know the radius of the noble elements, because you cannot actually make bonds with those, and you don't have covalent radius, you don't have metallic radius. Metallic radius you cannot have, so you don't have covalent radius because it doesn't exist as xenon 2 or helium 2. This doesn't happen. So that is why in that case we have another radius known as van der Waals radius of the element. Okay. So this figure 3.4a shows the decrease in the atomic radius when you go from left to right, and this here shows the increase in the atomic radius when you go from like down the group. So this is for the group 1 element and group 17 element. Actually, when you go from up like down the group, there are different trends followed in different groups. So here it is only mentioned for group 1 and group 17, that is the alkali metals and the halogens. So let us talk about the ionic radius. We already talked about the atomic radius, and now we are going to talk about the ionic radius. So let us talk about the ionic radius. So what do you understand by this term ionic radius? So here we are going to talk about the radius of cation or anion. So if you have a cation, then what would you expect your radius will be? Then your parent atom. Obviously in cation, you lose an electron to form cations, right? So you are losing an electron, but you are not losing any proton. So the nuclear charge remains the same, but the charge from the electron, that is the negative charge, decreases. So therefore, what you expect? You expect the decrease in size, more positive charge, that will hold the electrons more closer to it, and that is why it will decrease the charge. So the cationic radius is shorter than the radius of the parent atom. And just opposite to that, what about the anionic radius? So in case of anions, then you have negative charge, that is you have extra electron, but you don't have extra proton. Okay. So in that case, the positive charge, the negative charge is more in comparison to the positive charge, and hence there is not proper attachment of nucleus of attachment of electrons to the nucleus, and hence electrons are spread far apart, and that is why the radius increases. So that means the anionic radius is, in case of anions, the ionic radius is greater than the parent atom. So how you will define it as? So when you in the increasing order, you will have first the smallest radius will be that of the cation, then the parent atom, and then the anion. Okay. So here one example is given of the fluoride ion. So fluoride ion has, what do you expect? Fluoride ion obviously will have more radius than the actual like more. Will we have greater ionic radius than its atomic radius? Yes, that is true. So it has a radius of 136 ppm, whereas the atomic radius of thorium is only 64, like half of it. For example, the radius of sodium is 186, and its sodium positive charge will be obviously less. It is 95 pm. So that is the bigger one. So when we find some atoms and ions which contains the same number of electrons, so there is a term for them. They are called isoelectronic species. Okay, so all the species that have the same number of electrons in them, They are known as isoelectronic species. For example, O2 negative, F minus, Na positive, Mg2 positive. They all have same number of electrons, and that is equals to 10 if you count. Then you get to know that in all these four ions, number of electrons is 10. But they have same number of electrons, but their radius will be different. Why the radius will be different? The question is that you will, anyone can ask me that these elements have same number of electrons, right? So it should have similar, the radius of the atom should be similar, or the ion should be similar, but the answer is no for this, because the size of any element does not only depends upon the number of electrons in it, but also depends upon the nuclear charge. Okay, so you can see that all of these has different nuclear charges, right? So hence its radii will be different. So what do you expect? O2 negative to be like the maximum, right? And also, if you see nicely, then all of these elements are of the same period. Okay, so you can actually kind of compare them. So you all know that if you have more negative charge, then the radius is more. So here the biggest radius is that of the O2 minus, and the smallest radius is that of the magnesium 2 positive. So let us solve the problem number 3.5. Which of the following species will have the largest and the smallest radius size? Definitely, the largest size will be that of the parent atom, because all of the ions, whatever is given listed here, are cations. So the parent atom already have greater radius than that of the anion. So now you have to choose between magnesium and aluminum, which will have the largest size. So when you go from left to right, you have magnesium, then you have aluminum. Okay, so when you go from left to right in the periodic table, then what happens? The size decreases. So what will be the largest size will be that of the magnesium. And when you talk about the smallest size, then you have two cations here that you need to compare. Magnesium 2 positive and aluminum 3 positive. So in such cases, you need to know, you need to just see what is the maximum, where the maximum number of charge is there. So in here, 3 positive is the maximum number of charge. So aluminum is 3 electron deficient. So that is why it has this, it is the smallest one in the whole out of these 4 elements. So now let us talk about the ionization enthalpy. So a quantitative measurement of the tendency of the elements to lose an electron is given by its ionization enthalpy. Actually, we have already discussed this in the previous lecture as well, and we kind of know the trend, right? And also, it is again kind of linked with that of the radius. So when the radius increases, so there's more distance between the nucleus and the outermost electron that needs to be knocked out, and that is why the ionization energy also decreases. So you need less energy to ionize an electron, because there is more distance between the nuclear charge and the electron. So that is why you need less energy to work out that electron, because that outermost electron is not that much deeply in contact with the nucleus, because it is part of it. Okay, but so when you go from left to right in a period, then the size is decreasing, and hence you will need more energy in order to knock out the outermost electron. So when you go from left to right, the ionization enthalpy increases. Just opposite trend is seen when you go from from up to down in the period. Here the size increases, and that is why the ionization enthalpy will decrease. Okay. It represents the energy required to remove an electron from an isolated gaseous atom. So this is very, very important. Isolated gaseous atom. So ionization enthalpy is defined for isolated gaseous atoms. So such atoms that is not in contact with any other element, because when one event is when any atom is in contact with other elements, its properties tends to change. So the first ionization enthalpy for an element X is the enthalpy change for the reaction depicted in equation 3.1, right? So the ionization enthalpy is expressed in units of kilojoule per mole. We can define the second ionization enthalpy also, but definitely I think everyone knows that the second ionization enthalpy will be much greater than that of the first, and this has no exception to it because it is more difficult to knock out an electron from positive charge entity. Energy is always required to remove the electron from an atom, and hence ionization enthalpies are always present. This is very basic. And also, the second ionization enthalpy will be higher than the first ionization enthalpy because it is more difficult to remove an electron from a positive charged ions than from the neutral atom, I already told. So, in the same way, the third ionization enthalpy will be greater than that of the second, and so on. So, the first ionization enthalpy of the elements having atomic number up to 60 are plotted in figure 3.5. So, you can see figure 3.5. So, this is the ionization enthalpy for 1 to 60. So, okay. So, this is obviously kind of, you can easily plot this variation. The periodicity of the graph is quite striking. You can see there is some periodic trend in the graph that is being followed, right? So when you are going from top to down, then definitely the size is increasing and hence the ionization energy is decreasing. But when you are going from left to right, like down, so here what you're doing is that when you're going from left to right, then the size is decreasing and hence the ionization energy is increasing. You can see this increase. This is increase is because of the period, like going from left to right, and this decrease. This decrease is because of the top to bottom. Okay, like down the group trend. And this graph, we need to like really get to know what exactly this graph is talking about. I already discussed. So let us just read what is written over here. So the periodicity of this graph is quite striking. You will find maxima and the noble gases. Definitely, it's very, very difficult to ionize noble gases. That is why it acquires the highest maxima, and which have closed electronic shell configuration and very stable electronic configuration. And on the other hand, the minima occurs at the alkali metals, and their low ionization can be correlated with their high net. Yes. In addition, you will notice two trends. The first, ionization enthalpy generally increases as we go down the period and decreases as we go descend in the group. So these trends are illustrated in figure 3.6a and 3.6. So this can easily be seen. So there are some exceptions like boron, oxygen, and that thing that we are going to discuss. You will appreciate that the ionization enthalpy and atomic radius is closely related properties. I already told you, once you know the trend in the atomic radius in the group and the electronegativity trend also, then you will be able to define all the, you will get to know about the periodicity of nearly all the physical properties. So to understand this trend, we have to consider two factors. First is the attraction of the electron towards the nucleus and the repulsion of the electrons from each other. So we all know this, right? So the effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of the shielding and the spinning of the valence electron. So because of by the intervening core electron. This is so true. Okay. So the nuclear charge that is faced by the inner orbitals will be more than that of the valence shell or electrons. This is for sure because there are electrons in between the valence shell and the core nucleus, which will shield the nuclear charge. Okay, so the exact charge that is coming, that is faced by the outermost electron is not exactly the exact nuclear charge. It is the Z effective we call it, or we can call it effective nuclear charge. Because of the screening, it decreases. For example, the 2s electron in the lithium is shielded by the nucleus by the inner core 1s electrons. As a result, the valence electrons experiences a net positive charge which is less than the actual charge of +3. In general, shielding is effective when the orbitals in the inner shells are completely filled. So this situation occurs in case of alkali metals, which has single outermost ns electrons preceded by the noble gas configuration, and hence it has uh, so this is because of this, it is very much shielded, and hence it is very reactive, because the effective nuclear charge here is very less. But when you move from lithium to fluorine across the second period, successive electrons are added to the orbitals in the same principal quantum level, again the same thing, and the shielding of the nuclear charge by the inner core electrons does not increase very much to compensate for the increasing attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighs the shielding. Okay, so consequently, the outermost electrons are held more and more tightly, and hence the ionization enthalpy when you go from left to right also increases. And we already know that as we go down the group, the ionization energy decreases, and we know the reason for that. So from figure 3.68, you will notice that the first ionization enthalpy of boron is slightly less than that of beryllium, even though the former has a greater nuclear charge. So what is the reason behind it? So in order to answer any such questions about the periodicity or any physical property, you need to know the electronic configuration that was taught beforehand. So here you can see easily from this graph, you will say that boron, why is it here? It should be somewhere here, right? But it has lesser ionization enthalpy than that of beryllium. But we read that when we go from left to right in the periodic table, then the ionization energy tends to increase. But why there is that? It is that boron has, or oxygen in that case, also you have lower ionization enthalpy than the beryllium. So the answer to this will be very simple when you write the electronic configuration of it. Okay. So it is written over here, I guess. So boron has Z equals to 5, and it is slightly less than of beryllium, which is Z equals to 4. Okay. So we can consider same principal quantum number, quantum level, and S electron is attracted to the nucleus more than a P electrons. In beryllium, the electron removed from during the ionization is an S electron, whereas the electron removed from the ionization of boron is P electron. So the penetration of S is more to the nucleus than the P, and hence to take out electron from P requires lesser energy. Okay. And also, hence the 2p is more shielded from the nucleus by the inner core of, also obviously it is shielded also more from the nucleus by the inner core electron than the 2s electrons of beryllium. Therefore, it is easier to remove 2p electron from boron compared to the removal of 2s electron from the beryllium. Thus, boron has a smaller first ionization enthalpy than beryllium. Another anomaly is the smaller first ionization enthalpy of oxygen. Here you have nitrogen, where it is half filled p orbital is there, and also half filled p orbital also shield kind of properly, and that is why you will have slightly more like radius, and that is why you have. So let us read what is written. So this arises because in the nitrogen atom, 3 2p electrons resides in different atomic orbitals, obviously, whereas in the atomic oxygen atom, 2 of the 4 2p orbitals must occupy the same 2p orbital, resulting in an increased electron repulsion. So that is why in order to, it is easy for them to release an electron, because in this case, like in case of nitrogen, you have one single electrons in each orbital. There is no electron repulsion. But as soon as you go from nitrogen to oxygen, here you have one more electron added to the orbital, and now one orbital will always share two electrons, and that is why there will be repulsion, and which this is repulsion will result in the increasing radius, or we can say ease of ionizing the electron. So the first ionization enthalpy, the delta IH value for the third period elements, that is the sodium, magnesium, and silicon, are respectively these. Predict whether the first ionization enthalpy value for aluminum will be close to 575 or 760 kilojoule, and justify your answer. Aluminum comes after magnesium, right? So when you see the table, so it is talking about sodium, magnesium, aluminum, and silicon, and has already given the atomic radius of these three elements apart from aluminum. And now we need to know if it is asking that it will be closer to silicon or it will be closer to magnesium. So the answer to this is that it will be closer to that of silicon, right? Because in case of silicon also 2p orbital, 3p orbital is being filled. So let us see what it is written. It will be more closer to 575 kilojoule per mole. So the value of aluminum should be lower than that of the manganese because of the effective shielding of the 3p electrons from the nucleus by 3s electrons. So now the answer was wrong because we already know that the group 13 elements has lower ionization enthalpy than the group 2 elements. And the reason for this is very simple, because in this case you have lesser electronic repulsion, and that is why in case of group 13 you have lesser electronic configuration because electronic repulsion, because all the electrons are present in separate orbitals, and that is why shielding is also good. There is no orbitals empty, and that is why the size is greater and the ionization enthalpy is lesser. So the ionization enthalpy of aluminum will be lesser than that of the manganese, and also the ionization enthalpy of silicon will be very greater than that of what is asked aluminum. So it will be closer to that of 575 kilojoule per mole. So now let us talk about the last topic for this lecture, that is the electron gain enthalpy, and it is just opposite to that of ionization enthalpy. Here also we are talking about the neutral gaseous atom and converts into the negative ion, that is, you are taking up the electron right here. And to take up an electron, you need to lose your you need to lose the energy. Now let us, before going to the book chapter, we will just recall what we just read. So we read about the radius is that when we go down the group, the size increases, and when we go from left to right, the size is decreasing. So in order to gain electron, so when you have smaller size, so that in such cases the gaining of electron will be easier, because the nucleus and because the formed anion will have a smaller distance between the nucleus and the electron atom, and that is why we'll have greater electronic and nuclear attraction. So that is why it is this we can say that electron gain enthalpy will increase, that is in negative, okay? Or we can say, yes, it will increase when you go from left to right. Increase, you should almost know, and this is very common, that electron gain enthalpy is to negative. It is always negative. So if I'm telling it will increase, then it will increase in negative, like more energy will be released, that is more favorable electron gain enthalpy. So when you go from left to right, the electron gain enthalpy increases, and when you go from top to bottom, that is down the group, since the size is increasing, that is why the gain in electron will be difficult, and that is why the electron gain enthalpy will decrease. So here is some of the electron gain enthalpies of some of the elements, as you can see from group 1. Also, when you're going down the group, size is increasing, and hence there is electron gain enthalpy also decreases, and the similar trend is followed everywhere. But we are going from left to right, then you can easily see that since the size is increasing, and hence the electron size is decreasing, and hence the electron gain enthalpy will become more and more negative. But it is exception. We are not, when we're talking about all of these physical properties, we are not talking about group 18, because group 18 has a positive electron gain enthalpy because it doesn't like to take up electrons, doesn't like to give electrons. So it has exceptionally high ionization energy also, and exceptionally high electron gain enthalpy as well. So the last topic that we are okay. So let us take a problem 3.7. Which of the following will have the most negative electron gain enthalpy, and which is the least negative? So first, you need to know the position of these elements in the periodic table: P, S, Cl, and F. Phosphorus, silicon, fluorine, and F. Let's go to the periodic table. Okay. So this is phosphorus, sulfur, fluorine, and F. So when we are going from top to bottom, size is increasing, right? And when we are going from left to right, size is decreasing. So when you're decreasing the size, then what is happening? Electron gain enthalpy will become more negative, right? So here, like in these three, you know that Cl has the most negative electron gain enthalpy. But when you go from top to bottom, the size is increasing, and hence the electron gain enthalpy will be more lesser, right? But it is an exception with fluorine, because for fluorine, so in that case, in these three, Cl has the most negative, and in these two, fluorine should have the most negative, right? So let us see what is written in the answer sheet. As I told, that here is an exception, okay? So in case of fluorine, adding of electron, fluorine is very, very small atom, and it already has 7 electrons in its valence shell. So taking one more electron, since the size of the atom is small, that is why, which means that the orbitals are very close to each other, and adding one more electron to that already like kind of filled orbital, only one space is there. So there will be more electron repulsion and the electron nucleus attraction. So in this case, it is an exception where fluorine has the most negative electron gain enthalpy. So let us talk about the electronegativity. So I already told you that an atomic radius and electronegativity has everything, like every role to play. Now again, electronegativity is what? Like electronegativity of particular element is what? Like more electronegative an element is, more likely it tends to attract an electron towards itself. So if it is smaller, then the electronegativity will be more, and if it is bigger, then the electronegativity will be smaller. So it is very, very simple. And there are various scales given by very, very famous scientists in order to measure the electronegativity, because it is the characteristic of an atom, and all of these, surprisingly, all of this scale gives the electronegativity differently, because in order to define electronegativity of a particular atom, you need to assign electronegativity of a particular atom, and then with respect to that, like in comparison to that, you need to define the electronegativity of all the other atoms. So you have different scales to measure the electronegativity: Pauling scale, Millikan-Jaff scale, Alfred-Rochow scale. So Pauling scale is very, very famous, that we actually, I think, we consider. So Linus Pauling, it was an American scientist, and he assigned the value of electronegativity of 4 to fluorine, and then he approximated the values of all the other elements with respect to this. Okay, so he defined that the most electronegative element of the periodic table is fluorine, and assigned electronegativity of 4 to that element. So the electronegativity of any other element is not constant. It varies depending on the on the element to which it is bound, obviously. So though it is not a measurable quantity, it does not mean a predicting the nature of the force that holds a pair of atoms together, a relationship that you will explore later. So this is very, already I told you. So the electronegativity generally increases across the period from left to right and decreases down the group. Again, it has to do something with that of this size, okay? Knowing the relationship between the electronegativity and the atomic radius, you can now visualize the relationship between electronegativity and the metallic properties. And again, electronegativity and non-metallic properties is very on the same page, because as you increase the electronegativity of the particular element, you increase its non-metallic characteristics, or you increase its electron gain enthalpy, or you decrease its ionization enthalpy. So you need to like really this figure 3.7 is very important, and it tells everything whatever we studied till now. So now again we will be starting with a different topic, periodic trends in chemical properties. Till now we studied all the physical properties and its periodic trends. In the next lecture we will be studying the periodic trends in chemical properties.